The bill work here, we're integrating 1 over y dy, and remember that that this can also be written as y to the minus 1 dy. And so if we notice when we use the power rule, we bump up this negative 1 power to a 0, and then we divide by that, and that's undefined. So we have to recognize this antiderivative of 1 over y dy is the natural log of the absolute value of y plus c. And this is going to become really important when we're doing differential equations for exponential growth and decay for today. Today we're working with exponential growth and exponential decay. We're going to use a lot of what we learned in pre-calculus. So you're going to have to really tap into that that knowledge. So when we're talking about exponential growth and decay, all exponential models, the very basic exponential model follows that pattern. So here's our basic exponential model, and so this is the real general model, or the real basic model that we follow. And so when we're talking about then the components of this model, we're talking about this y sub 0 as being our start or our initial value. And as we've worked a bunch of initial condition problems, that should probably have new significance for you. That initial value, we'll see where that comes about today with our anti-differentiation. And then we also have to remember that back in pre-calculus, we acknowledged that our constant, our k value, when it's positive, it represents growth, and when our k value is negative, it represents decay. So that is this value right here. The value in the exponent there, that determines our growth and our decay. And then we have a final value here of y. So that's our final value there. And so if you notice, that was all pre-calculus. We learned that all in pre-calculus. So if we look at the calculus, the way we kind of apply this in calculus is that we get this exponential model by starting with a differential condition, and that differential condition is that the quantity y increases or decreases, so there's your k value, at a rate that's proportional to the amount present. So the amount present is quantity y. So if you notice then down here, if we kind of get the keywords here, we have it increases or decreases at a rate. So here is that rate, or that differential, and that rate increases or decreases. So we're talking about growth or decay. Here's the increasing if the k is greater than 0, and here's the decreasing aspect if k is less than 0, and that's the proportionality. So it increases or decreases at a rate that is proportional to the amount present. So here's the present amount. And so what we're going to see today is if we follow that differential model, as we take the antiderivative of that, we end up getting this this exponential function here. So if I asked you the question here, can you find the calculus stuff above? The calculus stuff above is right here. That's our differential expression that we're going to learn to take the antiderivative of. And so we can see this initial condition here that I was talking about a little earlier, where we have this as the initial value. And that again should have new significance to you since we've solved several differential equations and with initial condition problems. So what we're going to do here today is to solve that separable differential equation. So we're going to take those exponential type differential expressions, the dy dt equals k times y, and separate them and take their antiderivatives. Again, with just a little bit of a pre-calculus review, exponential growth looks something like this. And exponential decay looks something like this. And when we talk about exponential growth and exponential decay, really we're talking about it in terms of time. So that being the case, if you can kind of think about this in terms of time, then what we're kind of saying is let's get rid of this and this portion of those graphs, because time being less than 0 doesn't really have any physical significance. And then we're talking about, then we're starting the clock here, and so there's that initial value y sub 0. And then with our growth constant greater than 0, we see an exponential increase, and with our constant less than 0, we see an exponential decrease. So that's kind of our pre-calculus review there. So we're going to try this basic exponential problem here, having to do with the emerald ash borer. And the population of this beetle grows at a rate that is proportional to the amount present. So that is kind of the wording you have to look for to know that you would have, or you should be able to set up this differential expression. So this phrasing right here is very important. Okay, so it's growing at a rate proportional to the amount present, and that growth rate is 5/2. In other words, the the k value here is 5/2. And so if we start with 10 boring beetles and they reproduce exponentially, how many beetles do we have 3 months later? So we have our initial condition here that at time t equals 0, we have 10 insects. And so if we look at some of this data here, you can see over here that I found some data dealing with the emerald ash borer infecting trees. So if we look at the exponential growth here of trees that have died as a result of the emerald ash borer, we can kind of see that exponential growth. And so what we're going to do is we're going to take that differential expression dy dt equals 5/2 y, and we're going to separate the variables and go ahead and take the antiderivative of both sides. So we're going to divide by y here, and that's the same as multiplying by the reciprocal. And so then as we cancel out those terms there, we have 1 over y dy dt equals 5/2. So we're basically isolating this proportionality constant, and then we are relocating the differential dt to the right hand side, in essence kind of multiplying each side by dt. So we end up with a separable differential expression that looks like 1 over y dy equals 5/2 dt. And if you notice, this portion here on the left, 1 over y dy, is what we started the class with integrating 1 over y dy, because with exponential problems, this is the focal point. You will have to integrate or take the antiderivative of 1 over the variable. So as we take this antiderivative then, we end up with the natural log of the absolute value of y equals 5/2 t plus the constant. We usually put the constant on the right-hand side with the independent variable. And so we've got to solve for y, and in order to solve for y, we've done the calculus here. Really, the calculus is right here. Okay, at this point, we are looking at all logarithmic properties from this point forward that you learned in pre-calc. Okay, so we're going to take some time here to do all of these logarithmic properties. So in order to solve for y, we have to exponentiate both sides. And when you exponentiate a natural log, then that's the exponential identity of 1, so we just have the value y here. And then this is all now up in the exponent. So your law of exponents say that if I have exponents up here, that's really the same as saying e to the 5/2 t times e to the c. So if you kind of think about that, and this is just your law of exponents here. So that's nothing more than the law of exponents. Okay. We can add exponents when we have the same base. So in other words, if we had like 7 to the 3 plus 4, let's pick different numbers, 7 to the 2 plus 3. That's equal to 7 squared times 7 cubed. Okay, so that's the same as 7 to the 5th. So that's just your law of exponents, and this is really an algebra 2 skill here, if you remember back to algebra 2. Okay, but I know you can kind of forget about these skills, so that's why we're taking so long to go through them. So if we look at this then, e to the c, I'm going to call this c1 for the same reasons we talked about in the previous section. Euler's number is just about 2.7 something, and if we raise that to a constant, that's really just another constant. So in reality, we're talking about y equal e to the 5/2 t times a big constant, or more typically we write it like this. So that constant of integration just comes out in front. And so here is our general solution to the emerald ash borer problem. So now we know at the beginning, at time t equals 0, we start out with 10 beetles. Well, that we know that the initial value is just this value out front here. So if we solve this, if we put this in for y and put this in for t, we should be able to get a constant of integration here of 10. We know that this is the initial value from pre-calculus. So let's see if we come up with that using our initial value problem approach. So we put in y of 10 there, and that equals c e to the 5/2 times 0. E to the 0 is 1, so we get an integration constant of 10. So the particular then, the particular solution then for this beetle population is it's going to grow at 10 e to the 5/2 t following that function. So in 3 months, that beetle population that started at 10 beetles is going to be 10 times 5/2 to the times 3. Oops, I forgot the e. Is going to be 10 times e to the 5/2 times 3. And so if we calculate that out, we get Euler's number to the, that would be 15/2, and then times 10, we get 18,080 beetles. So if you think about going back to the top here, looking at that, you know, we had that constant of 5/2, we had the initial value of 10. Oops. If you notice, we had that, we can see that when we have this exponential, this really basic exponential of being growth or decay of being proportional to the present value. So whenever we see that phrasing, that phrase up here that I highlighted, rate that is proportional to the amount present, we should be able to jump right to the equation even without doing the separation of variables. Here is that basic expression that says it's growing proportional to the rate that is, the rate is proportional to the amount present. Okay, so that's a very basic exponential relationship. And so with the beetle, we had a differential equation that followed that very basic pattern. We had an initial value of 10, and we ended up with a exponential growth model that looked like that. Okay, so we should, if we know that, if we see that phrasing, we should know that that we shouldn't have to go through the separation of variables. So if we're looking at this, we have a rate that is proportional. A proportion is any constant here. So here's the proportionality. Here's the proportionality constant K. So we've got a rate that is growing proportional to the amount present. And we have an initial value here of 27. So we should be able to write the function, the exponential function directly, and with our proportionality constant being negative, then this must be a decay problem. Likewise, again, picking out the proportionality constant here, again it's negative, we have a decay, and here's our initial value, and so we should be able to just, with these really basic exponential growth and decay problems, pick out those two values and write it without doing any calculus whatsoever. And so this is kind of more of a pre-calculus approach. What happens when this pattern does not hold? Okay, so we have to recognize that we have this basic pattern. We have this basic pattern. This is where the rate here so this is where the rate is proportional to the amount present. So it's very characteristic. It's got a proportionality constant. That's a number. It's either positive or negative. And we have just a y over here. And so what happens when this basic pattern doesn't hold? So for instance, here's a differential equation. And it's exponential. We'll see that when we move this to the other side. But we don't have a rate, and we don't have just a y over here. We have something on the right-hand side that's more complicated. And so in this case, there's nothing else we can do. We have to do some calculus. We have to separate this, and we have to, and then take the antiderivative and treat this like any initial condition problem that we've done in the past. So to get our expression that has to do with a y, so this whole thing in the brackets has to come over to the other side. So we have 6 minus y. We're going to divide by that. That's the same as multiplying by the reciprocal, 6 minus y. And so we have 1 over 6 minus y dy. And I'm going to go ahead and I have an x over here with a dx. I'm going to bring the differential to the other side. So we have to take the antiderivative of both sides to find out what this differential equation looks like. We still have 1 over something. So just like the beginning of the, on page 1, the beginning of the lecture, this is still 1 over something. So we're going to end up with a natural log of something over here. It might be better served if we just go ahead and do our u sub here and call our u 6 minus y, like we would do when we were doing our u subsection. And then that means du dy equals minus 1, right? The derivative of this is minus 1. And so we end up with a du equals minus 1 dy. We need to substitute out just a dy. So minus 1 du equals dy. And so we end up then with an expression that looks like the antiderivative of 1 over u. So we're going to have 1 divided by u times negative 1 du on the left-hand side. And so bringing the negative 1 to the outside, we have negative 1 times the integral of 1 over u du. And that equals, on the right-hand side, we have to take the antiderivative of x dx. So the antiderivative of x is x squared over 2. And then we're going to put the constant of integration over here. And then we can go ahead and take the antiderivative of the left side. So we have minus 1 times the natural log of u, of the absolute value of u, equals x squared over 2 plus c. And we need to exponentiate. We know that after we substitute back in here. So minus 1 times the natural log of 6 minus y, the absolute value of that, equals x squared over 2 plus c. And before we exponentiate this, we need to get rid of this negative 1 out front. So all we're going to do is we're just going to take care of that algebraically. We're just going to go ahead and divide by a negative 1 and divide by a negative 1. And then that gets us natural log of the absolute value of 6 minus y equals negative 1 times the quantity x squared over 2 plus c. And the reason why I put that in brackets is I know when I exponentiate, that's going to become, this whole right-hand side is going to become a power. So I might as well just put it in brackets right away. So we're going to exponentiate both sides. Exponentiation of a natural log just gets us what's ever in the natural log location. So we end up with 6 minus y equals e to the minus x squared over 2 plus c. And so now I'm going to leave this 6 minus y over here, and I'm going to rewrite this e to the minus x squared over 2 times e to the minus c, and again this whole e to the minus c thing is just a constant. So that's going to come out front, and it's going to end up being c times e to the minus x squared over 2, and this is 6 minus y. So solving for y, I'm going to put y on this side, and so I'm going to bring this whole thing over here. So we have 6 minus e to the negative x squared over 2. So there is, and I forgot a c, let me squeeze a c in there. So there's my c, there we go. So, so there is my general solution. And so now we can go ahead and look at the particular, the initial conditions to get the particular solution. So the general solution looks like I go back up here, here's my initial condition of 0, 2. So if we know we have an initial condition of 0, 2, then if this is our general solution, then we have 6 minus c e to the minus 0 squared divided by 2 equals 2. So I went ahead and put in the 0 in for the x and the 2 in for the y. And e to this power is e to the 0, so that's just 1. So we have 6 minus c times 1 equals 2. And then bringing the c over here and subtracting the 2, we get 6 minus 2, which is 4. So our constant of integration is 4. So our particular solution then is 6 minus 4 e to the negative x squared over 2, and that equals y. I'll put the y over on this side. So there's that particular solution. So basically, we're looking at two big ideas here. One is that real general exponential solution, and then the other one is this more complicated solution that we do have to just end up separating and taking the antiderivative of both sides. I just wanted to remind you of the power rule, and I know I've put these up just about every day. This unit, we've got your basic power rule for integration. That's reversing the power rule for differentiation, and then the trigonometric integrals. Also a must know, and a must put in your calculator. See me if you want these in your calculator. I have made a program, and I can download those to your calculator if you want me to. And then we have our last homework assignment here of the unit. So this is the last assignment. So we have our proficiency checks for this unit of 6-1, and that's a day 1, day 2 thing. And then we have 2 proficiency checks for 6-2. We have a day 1, day 2, and we have a 6-2, day 3. That was the separable differential equations. And then we have this 6-4, day 1. That's the exponential growth and decay. So those are our 4 checks, and as you get those done, we'll check them off. And when you're ready to test, let me know. There's also a review sheet that's already in Drive for you to work on that will give you some AP level questions in preparation to take the summative. And then just a quick recap on this, on today's lesson. Today's lesson had 2 big ideas. We had that basic exponential growth / decay, where we had the rate that was directly proportional to the value, and then we had a more complicated exponential growth decay, where we had a more complicated differential expression. This is a must-use calculus, and this one was we can get the function right away just by knowing our initial value and our exponential growth or decay constant. So those are the two big ideas today.